projects. In this video, we are going to explain about the project title DTTSVM, a network intrusion detection method based on decision tree, twin support vector machine, and hierarchical clustering. Introduction. In modern cyberspace, the threat landscape is continuously evolving with an increase in sophisticated cyber attacks. Network intrusion detection plays a pivotal role in identifying and thwarting these attacks. It involves monitoring and analyzing network traffic to detect anomalous or malicious activities that indicate a security breach. Protecting sensitive information, maintaining system integrity, and ensuring business continuity are crucial aspects that rely on effective intrusion detection in complex network environments. Twin support vector machine is an extension of traditional SVMs known for their effectiveness in binary classification tasks. Twin support vector machine (TWSVM) optimizes two parallel hyperplanes to achieve better separation between classes, potentially improving classification accuracy. Its advantage over traditional SVMs lies in its ability to handle imbalanced datasets and potentially offer better generalization. While twin support vector machine (TWSVM) excels in binary classification, extending its application to multi-class classification is challenging. Twin support vector machine inherently works for binary classification and cannot directly handle multiple classes. Strategies like one against rest (OVR), one against one (OVO), and decision tree based methods have been explored to adapt twin support vector machine for multi-class scenarios. OVR, one against rest, treats each class as a binary problem. OVO, one against one, builds multiple classifiers for each pair of classes, and decision tree based methods use twin support vector machine at the nodes to handle multi-class scenarios. The project introduces a novel method named Decision Tree Twin Support Vector Machine (DTTWSVM) tailored specifically for network intrusion detection. This method combines the strengths of decision trees in handling complex classification problems and the powerful binary classification capabilities of twin support vector machines. DTTWSVM aims to accurately classify and identify different categories of network intrusions using this hybrid approach. A pivotal contribution of the project is the construction of a decision tree within the DTTWSVM framework. This decision tree is strategically designed to maximize separation at upper nodes. By doing so, it aims to reduce error accumulation during the classification process. This optimized decision tree construction enhances the model's accuracy in identifying various types of network intrusions by creating a more discriminative and robust classification structure. Objective. The project's primary aim is to create an effective method for detecting various types of network intrusions within complex network environments. This objective aligns with the need to enhance cybersecurity by accurately identifying and categorizing different intrusion categories that potentially compromise network security. The proposed method DTTWSVM Decision Tree Twin Support Vector Machine is introduced as a solution to achieve precise identification of different network intrusion categories. This method combines decision tree principles with twin support vector machines (TWSVM) to leverage the strengths of both techniques in accurately classifying intrusions. The project aims to construct a decision tree within the DTTWSVM framework. This decision tree construction strategy focuses on maximizing separation at upper nodes. By doing so, it aims to reduce error accumulation during the classification process. This strategic construction enhances the model's accuracy and robustness. The goal is to train individual twin support vector machines (TWSVMs) embedded within the non-leaf nodes of the decision tree. This approach ensures that each node in the decision tree is equipped with an optimized TWSVM model, collectively contributing to the overall optimal performance of the DTTWSVM model. The project assesses the performance of the developed decision tree twin support vector machine DTTWSVM method using benchmark datasets specifically tailored for intrusion detection. such as NSL KDD and UNSW NV15 datasets. This evaluation involves comparing the performance metrics of Decision Tree Twin Support Vector Machine DTTWSVM against other recently proposed network intrusion detection methods. This comparative analysis provides insights into the efficacy and competitiveness of DTTWSVM in detecting network intrusions. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of 55 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This initial step involves importing necessary libraries and packages such as Pandas, NumPy, scikit-learn, Seaborn, Matplotlib, and more into the project environment. These packages provide functionalities and tools for data manipulation, visualization, machine learning modeling, and evaluation. Exploring the dataset. The project involves exploration of two specific datasets, namely UNSW NB15 and NSL KDD. This step includes understanding the structure of the data, checking for missing values, analyzing statistical summaries, and gaining insights into the features and their distributions within the dataset. Data processing. This phase encompasses data cleaning tasks such as removing duplicate entries and handling any missing or inconsistent data points. Drop cleaning refers to removing columns or rows with irrelevant or redundant information that doesn't contribute to the analysis or modeling. Visualization using Seaborn and Matplotlib. This step involves visualizing the pre-processed data using Seaborn and Matplotlib libraries. Visualization techniques like histograms, bar plots, scatter plots, and heat maps are employed to gain visual insights into data distributions, correlations, and patterns. Label encoding. Label encoding involves converting categorical variables or strings into numerical representations suitable for machine learning algorithms. This step ensures that non-numeric data like categorical labels is transformed into a format that the model can interpret. Feature selection using mutual info classification. This phase focuses on selecting relevant features that contribute most to the prediction of network intrusions. Mutual information classification is a technique used to assess the strength of the relationship between features and the target variable, intrusion or normal, for selecting the most informative features. Appending selected features to X and target column to Y. Once relevant features are identified, they are appended to the X dataset representing the input features. The target column denoting intrusion or non-intrusion labels is assigned to the Y dataset representing the output or target variable for the model. Splitting the data to train and test. This step involves dividing the dataset into separate subsets for training and testing the machine learning model. The training set is used to train the model, while the test set is used to evaluate its performance and generalization ability. Building the model. This phase involves the creation and training of the DTTSVM model, Decision Tree Twin Support Vector Machine, combining Decision Tree Twin Support Vector Machine for network intrusion detection. The model is constructed and optimized using the pre-processed data to accurately identify and categorize different types of network intrusions. Training the model. In this phase, the DTTSVM Decision Tree Twin Support Vector Machine model, which combines Decision Tree Twin Support Vector Machine, is trained using the pre-processed dataset. The model learns to identify patterns and characteristics of various network intrusion from the labeled data. Flash framework with SQLite for sign up and sign in. It focuses on creating a user interface or authentication system using the Flash framework and SQLite for user management. User gives input. uses input data related to network traffic or configurations for intrusion detection purposes. This includes information such as network logs, traffic details, or specific parameters relevant to identifying intrusions. The given input is pre processed for prediction. The user provided input undergoes pre processing steps to make it compatible with the trained DTTSVM model. This involves data cleaning, formatting, and transformation to ensure it aligns with the model's input requirements. Final outcome is displayed through front end. The final outcome in this case is predicted classification or labels for network traffic data input by the user. Through a front-end interface, the predictions of detected intrusions are displayed, providing insights into the identified network intrusions based on the input data. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm is Twin Support Vector Machine 1. TWSVM1 Twin Support Vector Machine 1 represents a specific configuration or instance of Twin Support Vector Machine TWSVM. It operates based on the fundamental principles of TWSVM, optimizing two parallel hyperplanes for classification. This variant has specific hyperparameters, kernel functions, or optimization strategies tailored for a particular application. TWSVM1 has specific adjustments or optimizations aimed at enhancing its performance in network intrusion detection. It is fine tuned to handle class imbalances or noisy data prevalent in network traffic, contributing to more accurate detection of intrusion patterns. Twin Support Vector Machine 2. Similar to Twin Support Vector Machine 1, Twin Support Vector Machine 2 represents another specific configuration or instance of Twin Support Vector Machine. It has different settings or optimizations compared to Twin Support Vector Machine 1, potentially focusing on different kernel functions, regularization parameters, or feature transformations. TWSVM2 is experimented with variations specific to network intrusion detection. It explores different ways of handling complex network traffic data or aims to improve generalization across various intrusion categories. Twin Support Vector Machine 3. TWSVM3 is yet another instance or variation of Twin Support Vector Machine with distinct settings, parameters, or optimization strategies. It differs from Twin Support Vector Machine 1 and 2 in terms of its configuration, potentially exploring different combinations of hyperparameters or kernel functions. TWSVM3 focuses on specific enhancements or adjustments aimed at improving the detection accuracy of certain types of network intrusions. It is tailored to handle unique characteristics of network data or improve the model's resilience against noise or outliers. DTTWSVM Decision Tree Twin Support Vector Machine combines the principles of decision trees with twin support vector machines. Decision tree nodes embed twin support vector machine classifiers, aiming to leverage the strengths of both techniques. The decision tree structure helps to partition the feature space, and at each node, a twin support vector machine model is utilized for classification, enhancing the model's accuracy and interpretability. Decision Tree Twin Support Vector Machine is specifically tailored for network intrusion detection. It aims to improve the accuracy of identifying different categories of network intrusions by utilizing decision tree nodes embedded with Twin Support Vector Machine classifiers. SVM Support Vector Machine. SVM is a supervised learning algorithm used for classification and regression tasks. It finds the optimal hyperplane that maximizes the margin between classes, effectively separating data points. SVMs handle high dimensional data well and can work with nonlinear boundaries through the use of kernel functions. SVMs are versatile and effective in handling binary classification tasks, including network intrusion detection. They serve as a baseline model in the project, providing a comparative assessment of performance against more complex algorithms. ELM, Extreme Learning Machine. ELM is a type of neural network algorithm characterized by its single layer feed forward network structure and fast learning speed. It randomly assigns weights between the input and hidden layer, minimizing the need for iterative adjustments during training. ELM, Extreme Learning Machine, is known for its efficient learning and good generalization capabilities. ELM offers an alternative to traditional SVM based approaches in network intrusion detection. Its fast learning speed and simplified training process can potentially contribute to quick and accurate classification of network traffic for intrusion detection purposes. Stacking classifier RF plus MLP plus light GBM. Stacking is an ensemble method that combines multiple classifiers to improve prediction accuracy. In this case, it combines classifiers such as random forest RF, multi-layer perceptron MLP, and light gradient boosting machine light GBM. The idea is to leverage the diverse perspectives and strength of different classifiers to enhance overall prediction accuracy. Stacking different classifiers can be beneficial in network intrusion detection by harnessing the strengths of individual models. RF, random forest, MLP, multilayer perceptron, and light GBM contribute their unique characteristics to improve the accuracy and robustness of intrusion detection systems. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graph offer a visual breakdown of how a model performs across essential evaluation metrics. These are the comparison graph of NSL KDD dataset. This is the accuracy comparison graph. Here on the x-axis we have accuracy score and on the y-axis we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is a precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the F1 comparison graph. On the x-axis, we have F1 score, and on the y-axis, we have algorithm name. F1 score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm which is best performing in all the performance metrics will be used for prediction. In this project, we have also utilized UNSW NB15 dataset. These are the comparison graph of UNSW NB15 dataset. This is the accuracy comparison graph. This is the precision comparison graph. And this is the recall comparison graph. And this is the F1 comparison graph. The algorithms which is best performing in all the performance metrics will be used for prediction. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contain algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. These are Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, this localhost, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register, but I have already registered myself. So click on sign in link here. So here we need to enter the username and the password which we have created and then click on sign in button. We have logged in successfully. So here click on prediction link. So here we can see we are having two data sets. We can execute the project using these two data sets. First, we will execute the project using the NSL-KDD data set. So click on NSL-KDD. So here we need to enter all these parameters to predict whether intrusion detection is classified or not. Before entering the parameters, let us understand the parameters. So the first one is service, type of service involved in the network connection. Flag, flags used in the network communication. Example, S0, S1, SF. SRC bytes, number of bytes transferred from source to destination. DST bytes, that is destination bytes, number of bytes transferred from destination to source. Count, number of connections to the same host has the current connection. Error rate, percentage of connections that have SYN errors. Same SRV rate, percentage of connections to the same service. Different SRV rate, percentage of connections to different services. DST host SRV count, number of connections to the same service has the destination host. DST host same SRV rate, percentage of connections to the same service has the destination host. DST host different SRV rate, percentage of connections to different services than the destination host. DST hosts error rate, percentage of connections that have SYN errors to the destination host. Now we will enter the parameters. So I'm entering the parameters. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is DOS. Now we will enter another set of parameters and check whether attack is detected or not. So I'm entering another set of parameters now. So here I have entered another set of parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is probe. Now we will enter another set of parameters and check whether attack is detected or not. So I'm entering the parameters. So here I have entered another set of parameters. Now click on predict button. So here we can see the result. There is an attack detected. Attack type is R2L. Now we will enter another set of parameters and check whether attack is detected or not. So I'm entering the parameters. So here I have entered the parameters. Now click on predict button. So here we can see the result. There is no attack detected. It is normal. In this way, by entering the parameters, we can predict whether attack is detected or not. Now we will do the prediction using another dataset. So click on UNSW NB15 dataset. So here we need to enter these parameters to predict whether attack is detected or not. Before entering the parameters, let us understand the parameters. So the first one is duration. It represents the duration of a network connection, indicating the time the connection lasted. S bytes, that is source bytes, denotes the number of bytes sent from the source origin during the connection, measuring outbound data. D bytes, that is destination bytes, signifies the number of bytes received at the destination during the connection, measuring inbound data. Rate, transfer rate, refers to the data transfer rate or speed of the connection, often measured in bits per second. STTL, source time to live. It represents the time to live value for the source, indicating the maximum number of hops or routers a packet can traverse before being discarded. DTTL, destination time to live. Similar to STTL but for destination, indicating the maximum number of hops allowed for incoming packets. S load, that is source load, measures the data load in bytes per second on the source side, indicating the rate of data transmission from the source. D load, that is destination load, measures the data load in bytes per second on the destination side, indicating the rate of data reception at the destination. DINPKT, that is destination input packets, represents the number of packets received by the destination during the connection. S mean, that is source mean packet size, denotes the average packet size sent by the source during the connection. D mean, that is destination mean packet size, denotes the average packet size received by the destination during the connection. CT state TTL, connection state time to live, represents the number of connections observed in the same state, indicating the persistence of a specific state in the connection. Now we will write the parameters and check whether attack is detected or not. So I'm entering the parameters. So here I have entered all the parameters. Now click on predict button. So here we can see the result. There is no attack detected. It is benign. Now we will enter another set of parameters and check whether attack is detected or not. So I'm entering the parameters now. So here I have entered all the parameters. Now click on predict button. So here we can see the result. There is an attack detected. Attack type is Gafford combo. In this way, just by entering the parameters, we can predict whether attack is detected or not. Now click on sign out button here. The conclusion of the project: DTTSVM, Decision Tree Twin Support Vector Machine, combines decision tree structures with twin support vector machines for precise detection of various network intrusions, showcasing performance comparable to recent methods. DTTSVM's training involves subdividing the dataset based on labels and decision tree structure on train support vector machines iteratively, enhancing its ability to capture diverse intrusion patterns. Evaluating on benchmark datasets like NSL KDD and UNSW NB15 demonstrates decision tree twin support vector machines' accurate identification of network intrusion categories, validating its real-world effectiveness. DTTSVM, that is Decision Tree Twin Support Vector Machine, contributes as an intelligent and efficient defense mechanism against diverse network intrusions in complex environments, elevating network security measures significantly.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.